In this video, we are going to explore exponential functions and their graphs, and we're going to use the transformations of functions to graph our exponential functions. So our first set of XY charts is our function is given as 2 to the x. So I'm going to put in -3 where I see that exponent. So this is going to be 2 raised to the -3, but this is 2 raised to the -3 is the same thing as 1 over 8. So this is -3 goes in and 1/8 comes out. This is 2 to the -2, and that is 2 to the -2 is 1/4. So -2 goes in and 1/4 comes out. 2 to the -1, which is 1/2, so -1 goes in and 1/2 comes out. 2 to the 0 is 1 all day long, so 0 goes in and 1 comes out. 1 goes in, so 2 to the 1, which is going to give us 2, so 1 goes in and 2 comes out. And then 2 to the 2, so 2 and 4, and then 2 to the 3, which is 2, then 8. Now they're asking me to graph this, so I'll go ahead and put in my XY here. So this is X and this is Y. So I put in, I'm going to make these, this is 1, this is 2, this is 3, this is 4, but I'm going to put, I'll do these as 2, 4, so okay. So I put in -3, so it's right here is -3, and 1/8 comes out. So I'm pretty low. It's actually like way low right down there. And I put in, I'm close to 0. When I mean I'm way low, I'm close to 0. 1/8 is closer to 0 than it is to 1. And then I put in -2 and 1/4 comes out. So maybe there, but that's still closer to the 1/2 mark than it should be. I put in -1 and 1/2 comes out. I put in 0 and 1 comes out. I put in 1 and 2 comes out. So there we are there. I put in 2 and 4 comes out. So I'm up here. And so this is what the graph looks like for the exponential of 2 raised to the x. Now, when I put in the -3 into this function, double negatives make that 2 to the 3rd. So this is actually going to be -3 and 8 comes out. And then double the negatives make this 2 squared. So -2 comes in and 4 comes out. -1 goes in, so 2 raised to the -1. So 2 raised to the -1 becomes +1. So -1 goes in and 2 comes out. 2 to the 0 is going to give me just, 1 all day long. So 0 goes in and 1 comes out. Then 2 to the -1, so we know this is +1, but 1/2 comes out. And then I have 2 to the -2, so 2 goes in and +1/4 comes out. 2 to the -3, 3 goes in and 1/8 comes out. And we kind of knew that, right? Because we knew this is a transformation of graph because of the fact that I have 2 raised to the -x. If my original function f of x should be of the form ab to the x, then putting this -2 right there tells me I'm going to have a reflection over the y-axis. But let's go ahead and graph these. This is my y and this is my x. I have these multiples of 1. I go over 2 for 1 to just make it easier to graph. And then again, I'm going to go to that. So I know I'm going to put in 0 and 1 comes out. I put in 1 and 1/2 comes out. And then it continues down in this manner. I put in -1 and 2 comes out. I put in -2 and 4 comes out. And so that's what this graph looks like. And we knew that because of that negative on the exponent tells me that's a transformation of graph. It is a reflection over the y-axis. So that tells me here that if my a, which is my base, actually it's my base b, when b is between 0 and 1, that I am going to be decreasing. You're like, what are you talking about? Well, so 2 raised to the negative x is the same thing as 1 over 2 to the x. So this really tells me that my b is 1/2. I can think about that as being b to 1/2. So it's telling me that when my base is a fraction between 0 and 1, as this example, my base is a fraction between 0 and 1, it's going to be decreasing from left to right. And then when my base is bigger than 1, so my b is bigger than 1, I'm going to be increasing left to right from as x goes to positive infinity. Let me use the correct mathematical information here. And then, of course, we know that when this happens, when b is in this form, that it is decreasing as x goes to infinity. Okay, so the transformations of graphs that we know from 1.5 still hold true. And so some of the things that we know about the parent function, when I just have b to the x, I don't have an a as a coefficient. First of all, it's 1-to-1, which means it will have an inverse. There is a horizontal asymptote at y equals 0. The domain is everything. The range is 0, not included, up to infinity. Even if it's decreasing, even if my graph looks like this, I am decreasing, but I'm never actually going to go to 0. So I will be decreasing when I have a transformation of graph, but I'm always going to be above 0. So that's my range. The intercept, the y-intercept is 0, 1 for all of them without a transformation. And since the range is from 0 and above, that means I have no x-intercepts without transformations. And if my base is bigger than 1, we're increasing. If my base is less than 1 but bigger than 0, we are decreasing. So here's an example where we have a transformation of graph where we have a +3. Notice that this horizontal asymptote has gone up to y equals 3, and this point, which is the point 0, 1, moves up 3, so it goes to 0, 4. And then if I have -3, I take and drop this down by 3, so that point, the y-intercept, goes from 0, 1 to 0, -2. And my horizontal asymptote is at y is equal to -3. My horizontal translations, notice that the horizontal translations are in the exponent. And so I have a +3, we move back 3. So this point, which was right here, goes back 3. So now that point, the horizontal stays the same. Now that point is -3, +1. And then if I have this, which is 2 raised to the x minus 3, it moves it in this direction 3. So that point, which should have been 0, 1, now becomes 3, 1. And the horizontal asymptote is still y equals 0. Now we're going to start doing vertical stretches and vertical compressions. So with a vertical stretch, I have a 3 there, and my horizontal asymptote is still the same. And instead of going through the point 0, 1, since I know with a vertical stretch or a vertical compression, I multiply the y values by whatever the stretch or compression is. So this 0, 1 goes to the point which is 0, 3, because I have to multiply my y values by 3. Similarly, if I start at 0, 1 and I have a compression of 1/3, this point then becomes 0, 1/3, because I'm going to multiply my y values by that a out front, which is the shrink or stretch or the compression in the vertical direction. Now, horizontal compressions can still happen. They just look weird. Horizontal shrink, stretch, and compressions. The thing that what you should notice is that this still goes through when my exponent is not just x, it's 3x or 1/3 x, is that it is shrinking and stretching, or stretching and doing a compression as expected, but since we are multiplying or dividing each of the x values by that value out front, that they're all going to go through the 0, 1 unless I have a vertical shrink or stretch or a horizontal translation or a vertical translation for that matter. We are still doing reflections about the x and y axis, so you can see that I have 2 to the x's here, and then negative 2 to the x looks like this. And that is a reflection over the x-axis because we're multiplying all of our x's, all my outputs, not my x's, all of my outputs, all my y's by a negative 1. So we know that this is the point 0, 1, so we have 0, negative 1. When it's up in the exponent, we talked about this, it actually 2 to the negative x is 1 over 2 raised to the x, or I can write this as 1 over 2 to the x, that this does a reflection about the y-axis. So everything that we learned about transformations still hold true. So the way that we are going to see this in the parent function of b to the x is that we're going to have b raised to the x plus c plus d, where c is going to move it left or right, and since it's a plus 3, it's actually going to go left, and since it's a plus d, it's going to go up d. If we have an a value out there, then we're going to either have a stretch by a stretch by the absolute value, and you're like, why the absolute value? Because remember, there's a negative, it does a reflection. So a stretch when this a value, the absolute value is bigger than 1, and a compression when it's less than 1 but bigger than 0, the absolute value of it. Horizontal, if we have b, the absolute value of b, and this is a capital B, not the base B, I'm talking about cap B here, that if the absolute value is bigger than 1, it is a compression by 1 over the absolute value of b, and if the absolute value of b is a fraction between 0 and 1, then it is a stretch by 1 over b, because it does the exact opposite of what we expect. If the negative is in front of this lowercase b, it is a reflection about the x. And if the negative is up in the exponent, it's a reflection about the y. And the general translation would look something like this. And what we learned in 1.5 still holds true now. So, doing this point by point, and then we can talk about how we could just go right to what the shape looks like. This is going to be 2 to the negative 3 plus 1. In fact, I'm going to scroll right in here so I can get more space so you can see a little bit better. So this is 2 raised to the negative 3 plus 1, which is 2 to the negative 2. So negative 3 goes in and 1/4 comes out. So 2 to the negative 2 plus 1, which is 2 to the negative 1. So negative 2 comes out and negative 2 goes in, 1/2 comes out. 2 to the negative 1 plus 1, which is 2 to the 0. So negative 1 goes in and 0 comes out. 2 to the 0 plus 1. So we have 2 to the 1. So 0 goes in and 2 comes out. 2 to the 1 plus 1, which is 2 to the 2. So 1 goes in and 4 comes out. 2 to the 2 plus 1, which is 2 to the 3rd. 2 goes in and 8 comes out. And then 2 to the 3 plus 1, which is 2 to the 4th. So 2 goes in and 16 comes out. Now, when I go to graph this, let me come out just a little bit. When I go to graph this, I could have graphed this by just doing the translation. Now, this plus 1 means that I'm going to pick up my graph and it's going to be left 1 unit. So instead of going through this point right here, it's going to go back 1 to this point, and this is y and this is x. And so instead of going through the point 0, 1, it's now going to go through the point negative 1, 1. And instead of going through the point 1, 2, it's going to go through this point. So this is moved back to the point 0, 2. And you can see that this looks something like that. So I could have done it by the translation and instead of doing it point by point. And so now we're going to do this by the translation rather than do it at point by point. So the negative here means that we are going to reflect over the x-axis. And this plus 1 where I see it is going to mean that I'm going to go up 1. So here is my original one. I'll do it in blue. So it's going to look something like this. And then 4. So it's going to look, there's my original function. This is f of x is equal to 2 to the x. Now I'm going to go up 1. So my horizontal is at y is equal to 1. This point, which was at 0, 1, would have gone to 0, negative 1, but it gets moved up 1. And so it's going to look something like that. So that's what f of x is equal to negative 2 to the x plus 1. Now, this graph, we have a lot of things going on. So 3 is a horizontal stretch. So this is not a horizontal stretch, excuse me. It is a vertical stretch. By 3. This is left 1. And this is up 1. So I'm just going to take some points. Like I know my one of my points is 0, 1. This would have been on my original function. And I also know that I would have had 1, 2. And I also would have had, let me do negative 1 and then 1/2. So I'm going to do it by transformations with those points. Okay, so first thing we know is that we always do what's inside the function. So we're going to take all of my x's. I'm going to take all of my x's. I'm going to take and subtract off that 1. So now this is negative 2, 1/2. This becomes negative 1, 1. This becomes 0, 2. And then I could have put 2, 4. So this would have gone to the point 1, 4. So that's where those transformations went to. Now I'm going to do the multiplication by 3. So I'm going to take all my y's and multiply by 3. So negative 2 didn't change, negative 1 doesn't change, 0 doesn't change, 1 doesn't change. This becomes 3 over 2. This becomes 3. This becomes 6. And this becomes 12. And then I'm going to go up 1. So now I'm going to do the y's plus 1. Negative 2 doesn't change. Negative 1, 0, and 1 doesn't change. So 3/2 is 1.5. So I'm now going to go to 2.5. So 2.5. This goes to 4. This goes to 7. And this goes to 13. All right. So here is my y. Here is my x. My horizontal asymptote has moved up 1, so that becomes y is equal to 1. The point which should have been at 0, 1 goes to negative 1, 4. So negative 1, 1, 2, 3, 1, 2, 3, 4. So this is where the point, I'm going to call this point A. That's where that point A landed. This point, actually, indecision. Let's call the first one A. So let's go back and call this one A. So the point which would have been negative 1, 1/2 goes to negative 2. So I'm going to go negative 2 and 2.5, which is right about there. So we're going to call this A. This is where point B went to. So this is A. This is B. C was 1, 2 goes to 0, 7. It's 4, 5, 6, 7. So that's where C is. And then the point D, which would have been 2, 4, goes to 1, 13. So it's way up here. And this is what my graph looks like. And I did it by plotting points, by doing the transformations of points versus filling in this chart. So now that we know all this information, let's make a connection between these bases and these multipliers out front. Now, anytime I have a base, let me zoom in. Anytime I have a base that is a fraction or a decimal between 0 and 1, then I know that these are going to be decreasing. So I know this one's decreasing. This one's decreasing. And this one is decreasing. So I know that these have to be, that this F, this C, and this A have to be A, B, or C here. So now I'm going to pay attention to the coefficient out front. This is a coefficient of 4. These are coefficients of 2. So since this is a coefficient of 4 right here, then I know that it has to have a vertical stretch of 4, which means that instead of going through the point 0, 1, it's going to go through the point 0, 4. This C is the one that is decreasing and going through about 0, 4. So this C happens to be F. So this one is C. This is F. Now then we have to figure out what's happening with the 0.69 and the 0.81. We know that it's either B or it's A. They both have a coefficient of 2, so they're going to both cross at the same place. Well, the closer you are to 1, the flatter the graph is. So 0.8 is closer to 1 than 0.69, so this C has to be A. So this has to be C. That means this has to be D. Excuse me, that has to be A. And you're like, how do I know that? Well, if you were to do 2 times 0.81 to the 1, this in your calculator is going to be 1.62. If we were going to do 2 times 0.69 to the 1, this is going to be 1.38. So as we come over here, here's approximately 1. That 2 times 0.81 is 1.62, so that would be this one. And then 2 times 0.69 is 1.38, so that would be that one. And then once we get on the other side, so we're at -1, then when you put those in your calculator, the one with the 0.69 is going to be a larger number than the number that has the 0.81. So you can confirm that with your calculator. Now, we've talked about the ones that the bases are between 0 and 1. Let's talk about these whose bases are actually bigger than 1. Okay, so these three. So these three we know are all increasing. This one, this one, this one, and this one. This is the only one that has a 4 as a multiplier. So that has to be this one. This has to be D. D has to be D. It's the only one that is going through about approximately 4. So then we just have to figure out what's happening between this one and this one. Now remember, the closer your number is to 1, the flatter it is. And I know that this one is 1.28, is closer to 1 than 1.59. So, and again, you can confirm this with your calculator, but since the 1.28 is flatter, that one has to be B, and then the one that is 1.59 is the base, that one is E, so E is E. And that's just by looking at the coefficients out front, the bases, and you can confirm that with putting a couple of points in there, put in a 1 to see what happens. So then on this example, all of the functions have the same form, a, b to the x. Which graph has the largest value for b? Which one has the smallest value for b? Which graph has the largest value for a? And which graph has the smallest value for a? So we know that the graphs that are closest to 1 have the flattest shape, right? So the graphs that are closest to 1 have the flattest shape, whether it's increasing flat or decreasing flat. So if we look at these and we say, okay, well, A is got to have a small base. It's flat, it's close to 1, but B and C, there also must be fractions. You must be B values that are between 0 and 1. This is the one that's closest to 1. The one that is the steepest one looks like it's going to be C, because C looks like it's really steep compared to B, especially when B and C come together to the same place. So C would probably have the smallest one, the closest to 0. So we think the one that has the smallest value is graph C. Now, similarly, the flatter it is, the closer it is to 1, the steeper it is, the further away from 1 it is. So, and in the positive infinity. So D has to be the one that has the biggest B value. Now, the A value is going to affect the stretch. And so in the vertical direction, it's going to affect where it's crossing the x-axis. So this is the highest point on all of these. And since this is the highest point, this one has to have the highest A value, the largest vertical stretch. So the one that has the largest A value must be C. And then the one that has the lowest A value would be the one that is the lowest, because the A value affects the vertical direction, it's a vertical stretch, must be F. And so that's how you tell by the transformations. Transformations are terribly important. And that's it for this video.